and welcome to Accelerating Big Data Analytics Applications with FPGAs and OpenCAPI. My name is Peter Hofstee. I work at IBM in Austin, Texas, and part-time at Delft Technical University in the Netherlands. So after discussing what makes computers better and motivating the use of accelerators and talking about how accelerators can be integrated in systems, in this submodule we'll talk about a few accelerator examples. As we run through the examples, we will see that in many cases latency matters more than you might think. Accelerators are not just about improving throughput. So here are the three examples we'll use in this submodule, and some of these we will revisit in more detail later. The first one is compression or decompression of data. The second is high frequency trading. And the third is acceleration of regular expression evaluation. So the first example of acceleration that we'll look at is decompression or compression. Even though one thinks of this as a streaming application, latency often matters more than you might think. And it's actually at two levels, both within the application itself and also in how it's integrated. So if we look at compression itself, a very common scheme is Lempel-Ziv style compression, where we have our source code that is turned into the compressed sequence, where we have two types of tokens, literals, which basically just copy a certain character or sequence of characters to the output stream, or copy tokens, where you refer back to the already decoded stream or the stream to be decoded, and the output includes a reference to an earlier occurring sequence. The literals and copy tokens themselves may be further compressed with something like Huffman coding or things like that. But this is how it fundamentally works. So, clearly, when you decode such a sequence, especially if the tokens are of variable length, as they typically are, in order to know where the next token starts, you would need to know where the previous token ends, and that introduces a sequential dependency. Also in decoding, obviously, if you have a copy token, then in order to be able to copy the already decoded output to the output again for a copy token, there is a sequential dependency there as well, though typically not as severe one. You typically see two schemes that are either sort of byte-oriented, like Snappy, and on text, character text, they may achieve typically something like a 2x compression rate, or bit-oriented, like gzip, that may on text like books or so might achieve a 3x compression rate. Where might you integrate a compression or decompression accelerator? Well, you can do it near storage or near memory, which has the benefit that the application or the processor does not need to know about it, but the downside that the interface between the processor and the storage device, be it storage or memory, does not benefit from the compression, only the storage capacity does. Similarly, on the network, the key benefit is that you need reduced bandwidth on the external network, and you might improve latency if you have a lot of data to send. The downside is that because with networks, unlike with storage like memory that might be a part of the computer itself, you have less control over what happens on the other side of the network, and therefore standardization is required to ensure that what you do on the compression side can be decoded on the decompression side. And this does not only include the compression or decompression protocol itself, but also error handling, etc. Finally, you can have a CPU, an accelerator that is integrated with the CPU. And the key benefit here is that you can use that accelerator for a variety of purposes and a variety of attached devices. The downside is that you have as much acceleration as you've integrated with the CPU, which can be either over provisioning or under provisioning what you need. So a few observations. So first, latency actually tends to matter a lot in decompression or compression. So in decompression, it's obvious that if you have a long compressed file, because of the copy tokens, the output depends on what you processed before, and therefore it's difficult to parallelize. But even when a compressed text may be partitioned in chunks and the chunks compressed individually and decompressed individually, which introduces concurrency, it is still the case that in many cases you will find that software has been constructed, assuming that the compression is done on the CPU itself, and invoked on rather small pieces of text, for compression or decompression. And in that case, if the integration of the accelerator isn't very efficient, the round trip time can defeat the purpose of having the accelerator in the first place. Compression acceleration is going mainstream. It was introduced on FPGAs in IBM systems. Z enterprise data compression in particular, and it's now integrated in IBM's mainframe and power processors, and you will find compression acceleration integrated on the CPU on upcoming x86 processors as well. Our next example is high frequency trading. So obviously this is an example where latency matters a lot. People have spent enormous amounts of money creating networks with the lowest possible latency between exchanges. And when you're looking at a single exchange, a premium is paid to place your computers as close as possible to the exchange itself, reducing latency. What you try to achieve here is the lowest possible, what they call tick to trade. A tick is a piece of information, for example, that a certain stock has been sold at a certain price. And a trade is a buy or sell offer. And obviously, those who can react the fastest gain an advantage. So this is, again, clearly a case where latency matters a lot. It looks in a bit more detail at how a low latency solution may be architected. A packet comes in from the network, gets decoded in the accelerator and, for example, routed based on its stock symbol. Then a predefined action is looked up in a table, for example, a buy or sell offer if the price hits a certain value. And step 3 is to send the trade to the exchange market. In parallel, another entity, and this is often a CPU, might run prediction or strategy algorithms. So clearly, in this example, accelerators can provide a benefit and give you a faster turnaround time. However, especially, as more of the strategy elements may be included in the accelerator itself, programming the accelerator becomes more of a challenge. And in the most advanced trading algorithms may change, at a very high rate. Not only do the values change in response to changing market conditions, the trading algorithms and strategies themselves might change, and therefore, programmability is actually a serious issue, even with such highly optimized designs as accelerators, for high frequency trading. So our last example of acceleration is the evaluation of regular expressions. So regular expressions are common in queries and are often used to filter large amounts of data for the occurrence of certain words or symbols, perhaps in a certain proximity to each other. So FPGAs are very good at for evaluating regular expressions and order of magnitude more efficient than CPUs. And therefore, this is a good use of accelerator. Looking at an example of regular expressions in a bit more detail. So imagine that I may have just become interested in a certain combination of words, and I want to search a large data set, say the record of all the text on the internet, for that specific combination of words and symbols. And this might be a combination that, because of some news event, has just become of interest to me. And of course, the more words or symbols are involved in this search, the less likely it is that I would have been able to build an index of the occurrence of those words ahead of time. So this is also a good example of an opportunity for a near storage accelerator, but that of course does depend on having the storage in a searchable and non-encrypted format. So what are some of the issues we might run into when we design an accelerator for regular expressions? Well, first, the regular expressions may often be embedded in larger complex queries, and not all attributes of those complex queries may be able to be evaluated on an FPGA, say if I use the FPGA as an accelerator. Also, from data size, the complex query may exceed the capabilities of the accelerator, for example, because it uses a dictionary or some other structure that doesn't fit on the FPGA. So what we would like is to be able to smoothly, use the resources on the host CPU and system, as well as the resources on the accelerator, and interoperate between the two, alternating execution on the host CPU and the accelerator. And once again, in that kind of a context, the amount of latency that is incurred when you invoke the accelerator is of utmost performance, because you may be switching back between the accelerator and the host CPU very often. So in summary, I've given a few examples here of accelerators and where they might be effective to either provide increased throughput or reduced latency. And we've touched on some of the challenges. Integration with existing applications, often leads to issues with granularity, and that in itself can cause a need for low latency in the accelerator itself and how it's integrated with the CPU. And the second challenge we talked about is that some designs require frequent change. And in this context, as well as in general, it is important to make it easy to develop for for the accelerator and smoothly interoperate between the accelerator and the host CPU. So these challenges are ones that an OpenCAPI type interface between the accelerator and the host CPU can be helpful for, and that's what we will talk about in module number 2.